Okay class, come back to second lecture on geometrical isomerism, right? So in the first lecture, we covered about alkene molecules and oximes, aldoximes and ketoximes like that, okay? Now in this class, we are going to cover cyclic compounds like cycloalkanes, allenes, biphenyls and spiro compounds, okay? First, let me explain about cyclic compounds, simple cycloalkanes without any double bond. Now simple cycloalkanes. What are the examples for cycloalkanes? Now best examples for cycloalkanes are, yes, best examples for cycloalkanes: cyclopropane, cyclobutane, cyclopentane, next one cyclohexane, cycloheptane, cyclohexane, after cyclohexane, cycloheptane, seven membered ring system. And what is the structure of cyclooctane? 8 membered ring system, like that, okay? Now these are the simple examples for cycloalkanes. Up to 8 membered ring system enough, right? Now in cyclic compounds, how we are explaining geometrical isomerism? So first of all, what is the important condition to exhibit geometrical isomerism? Restricted CC bond rotation. Just you look at this 3 membered ring system. Now in 3 member ring system, how many carbon atoms are there? We have 3 carbon atoms, and all three carbon atoms here sp3 hybridization, okay? sp3 hybridization. Why? Because now in this ring system, if you are taking 2 bonds here, what is hybridization of this carbon atom? sp3. Again here also 2 hydrogen atoms are there. What is the hybridization? sp3. 2 hydrogens. What is corresponding hybridization? sp3, right? Now this is our 3 member ring system, and each carbon atom hybridization sp3 hybridization. First we are looking for CC bond rotation, just like alkene molecules and oxides, right? Now in 3 member ring system, sorry, not only 3 member ring system, any cyclic compound, even in the absence of pi bond, there is no chance for CC bond rotation. That you can understand from the real molecule, okay? This is our real molecule. Now here CC bonds are there, carbon 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 bonds, right? Even in the absence of pi bond, there is no chance for CC bond rotation. Here CC bond rotations are restricted or not. CC bond rotations are restricted. That's why now we can apply geometrical isomerism in cyclic compounds. That is the first condition, right? Next one, on the basis of proper substitution, now we can say that the given molecule can show geometrical isomerism or not, like that, okay? First I am taking these molecules, and we know that here CC bond rotations are restricted and there is no problem from the first condition, right? Next one, what is the second requirement condition for geometrical isomerism in cyclic compounds, right? Just I am taking like this. I am starting with 3 member ring system. Now 3 member ring system, clear, okay? Here the condition is at least minimum 2 sp3 carbon atoms. We have substitution like in alkenes. For example, here I am taking like this substitution. Yes, 2 sp3 carbon atoms I am selecting. Minimum 2 sp3 carbon atoms. Very easy to identify these molecules. No problem. Just wait 5 minutes. Then after that you can say whatever the molecule given. Now you can say that that molecule can show geometrical isomerism or not. Here I am taking like this, one of the substitution A and B, A and B, and come here A and B, A and B. So we have no problem with CC bond rotation. Why? Because here CC bond rotations are completely restricted, just like alkenes. And what is the second condition? We need proper substitution to exhibit geometrical isomerism. Okay, just you select now 2 carbon atoms, sp3 carbon atoms. Just like alkenes, just you verify now type of substitution present on this carbon atom. For example, if you compare between A and B, what is hybridization of this carbon atom? sp3. If you compare these two same or different? A is not equals to B. They are different from each other. A is different from B. They are not identical. And come to right side, again we have A and B substitution. Again here these two groups same or different? They are different, okay? At least on 2 sp2 carbon atoms, whatever the ring size, 3 4 5 6 7 8 member ring, whatever the ring size, to exhibit geometrical isomerism, at least at minimum 2 sp3 carbon atoms we have substitution like this. That is a minimum condition, okay? Now here A is not equals to B, A is not equals to B, right? So now here this molecule can exhibit geometrical isomerism. Here I am not going to write any cis trans isomers and all these things, that we will see later. Here the first thing is that when the given molecule will exhibit geometrical isomerism or not, what are the conditions for that? Okay, now first condition, cc bond rotations are restricted, and what is the second condition? Proper substitution like this, right? For example, if you are taking like four member ring system, four member ring system, yeah. Now this is our four membered ring system. Here we have how many sp3 carbon atoms? Here we have four sp3 carbon atoms. Now in order to keep the substitution, so what carbons we are selecting? At least two different carbons you select. Now here I'm taking like this 1, 2, 3 and 4 carbon atoms. Either you can select 1, 2 carbon or 1, 3 carbon. 1, 2 and 1, 4 are identical. Now you can select either 1, 2 carbon or 1, 3 carbon atoms, right? Okay, fine. Here, one second. This is my molecule, four member ring system, right? I am trying to keep substitution at these carbon atoms like 1 and 2 carbon atoms. What kind of substitution we require? Just like A and B. Next one, here also A and B or C and D, whatever it may be, minimum 2 carbon atoms, sp3 carbon atoms we require to exhibit geometrical isomerism, right? These are the two sp3 carbon atoms. Now just you check it. Here A and B groups are there, right? What is the relation between these two? Identical or non-identical? No doubt A is not equals to B. And come to this one, C is not equals to D. C is not equals to D. Same as alkenes. Now this molecule can show geometrical isomerism. Okay, right. For example, if you are taking same four member ring system and substitution, if you are taking at 1 and 4 position, something like this, okay, 1 and 4 position, here something like I am taking x and y, next one here also x and y, whatever the substitution given, whatever the nature of the groups. Now just to compare between x and y, same or different? X is different from y, and here x is different from y, x is not equals to y. And how many sp3 carbon atoms we are selecting? Sp3 carbon, again sp3 carbon atom. On sp3 carbon atoms, if you have different substitution, then this molecule can show geometrical isomerism. That is a story about four member ring system. For example, if you are taking five member ring system, like now this is our five member ring system, okay. Now here 1, 2, 3, 4, 5 carbon atoms are there. At any two carbon atoms, either adjacent or non-adjacent. Now just if you are taking substitution like this, yeah, here and there A and B, next one here A and B. What about geometrical isomerism in this molecule? Again just you come to this sp3 carbon atom. Don't think about other carbon atoms. What is the reason? There two hydrogen atoms are there on each carbon atom. Here there are two hydrogen atoms, two hydrogen atoms. Again here also by default two hydrogen atoms are there. Now with the help of these carbon atoms we cannot produce geometrical isomerism. Why? Because there are identical groups. Now we are selecting these two carbon atoms, 1 and 2, these two carbon atoms, and just you check these two groups, A is not equals to B. Yeah, it is okay. And come to this one, here also A is not equals to B. Your condition is satisfied and your molecule can show geometrical isomerism, right? So randomly I am giving few molecules, from that identify which molecule can show geometrical isomerism. Here our question is this is our question. Which of the following molecule can show geometrical isomerism? Which of the following, which of the following molecule shows or can show geometrical isomerism? That is our question. So randomly I am giving molecules like this. First I am going to start with three member ring system. Okay, here I am taking methyl and methyl, methyl and methyl. Again same three member ring system. Here I am taking methyl, methyl and methyl. Okay, and three member ring system, somewhere methyl, next ethyl group is there, and four member ring system. Here I am taking ethyl, next one ethyl, 1 2 position. Even you can take same ethyl groups at 1 3 position. Next one 5 member ring system, just I am taking like this, right? And again same 5 member ring system. So on one carbon atom methyl, here you can take ethyl group, maybe identical or non-identical, that's not a what problem, right? And here I am taking here ethyl group and here ethyl group, like that. Okay, so these are the given molecules. From these molecules just you try to identify which molecule can show geometrical isomerism, right? Fine. Come to first molecule. What about geometrical isomerism in first molecule, right? So here by default on this carbon atom, so actually what is the substitution given on that carbon atom? Methyl group. Here whenever there is a CH2, you completely forget about this carbon atom. We don't want that carbon atom. That is not used in geometrical isomerism because of the presence of identical groups. And come to this sp3 carbon atom. Already methyl group is given. By default, what is the fourth valency here? Hydrogen. Next one, methyl group is given. What is the fourth valency? Hydrogen. Methyl and hydrogen. Same or different? They are different. Next, methyl and hydrogen. Same or different? They are different. This molecule can show geometrical isomerism. Okay. Come to next example. Here, for example, sp3 carbon and sp3 carbon atom. What is the group already given? Something like methyl group is given. And what is the fourth valency? Hydrogen. Fourth valency hydrogen. Okay, right. One second. Yeah. Methyl group. Fourth valency hydrogen. Here already methyl group is given. Okay. And what about this one? Hydrogen. So now methyl and hydrogen different. Here hydrogen and methyl different. This molecule can show geometrical isomerism. Not only these two carbon atoms. For example, 1, 2, 3 carbon atoms. You can select 1, 2 or 1, 3, 2, 3. Not a word problem. Okay. This molecule can exhibit geometrical isomerism. Come to this molecule, we don't want this carbon atom. Why? Because here identical hydrogen atoms are present. They are helpless for geometrical isomerism. And come to these carbon atoms, two carbon atoms are there. Verify substitution at this carbon atom. By default, what is the fourth valency? Hydrogen. Already what is the group given here? Methyl group is given. And what is the name of this group? Ethyl group. And what is the fourth valency? Hydrogen. Now compare between hydrogen and methyl. Same or different? They are different. Hydrogen and this ethyl group. Same or different? They are different. So this molecule can show geometrical isomerism. Okay, right. Now come to next example. Now there is no use of these two carbon atoms. No use. And come to remaining two carbon atoms. Here at this carbon atom, what is the substitution? Ethyl. Here also ethyl. What is the fourth valency? Hydrogen. And fourth valency? Hydrogen. Ethyl, hydrogen. Same or different? They are different. Next one, ethyl and hydrogen. Same or different? They are different. This molecule can exhibit geometrical isomerism. Okay, right. Come to this one. So we don't want these two carbon atoms. Why? Because they are having two hydrogens. Now select this carbon and this carbon atom. What is the group given? Ethyl group is given. What is the fourth valency? Hydrogen. Ethyl and hydrogen. Same or different? Different. Here ethyl and this fourth valency, hydrogen. Same or different? They are different. This molecule also shows geometrical isomerism. Okay, clear. Now come to this one. There is no use of these three carbon atoms. Why? Because on each carbon atom, two identical hydrogen atoms are there. They are not useful in geometrical isomerism. Okay, come to next carbon atoms. Here there is no problem with this carbon. Yes, methyl group is given. And what is the fourth valency? Hydrogen. These two are different. But here CH3 and CH3. These two groups, same or different? Same. So because of that reason, we cannot produce geometrical isomerism. Minimum two carbon atoms we require for geometrical isomerism with the proper substitution, just like alkenes. Okay, right. No use of these three carbon atoms. Come to these two carbon atoms. In the given molecule, already there is a methyl and fourth valency hydrogen. Here there is ethyl group, and what is the fourth valency? Hydrogen. Methyl hydrogen different, hydrogen and ethyl groups are different. Then what about geometrical isomerism? Yes, now this molecule can show geometrical isomerism. Come to next example. We don't want these three carbon atoms, just we want these two carbon atoms. Why? Because some substitution is given. What is the given substitution? Ethyl. By default, what is the fourth valency? Hydrogen. Next one, at this carbon atom, ethyl is given. What is the fourth valency? Hydrogen. Okay. Ethyl, hydrogen different, hydrogen and ethyl different. This molecule can show geometrical isomerism. Yes. Come to next example by using what? 6-member ring system. So just identify geometrical isomerism possible or not. One 3 position, 1 4 position. For example, molecule given like this. Okay. So here we are not going to calculate number of geometrical isomers. That is the different topic. Just here we are trying to observe which kind of molecule can show geometrical isomerism. Yes. Bromine and bromine. For example, here something like bromine and chlorine is given. These are the given molecules. From that, identify which molecule shows geometrical isomerism. Yeah. So let us start from first molecule. For example, here if you start from this carbon, these 4 carbon atoms containing identical hydrogen atoms, no use. Or come to this carbon atom, sp3 carbon atom. So these groups same or different? Methyl and methyl, same groups are there. Here also same thing, methyl and methyl, same groups are there. There is no use, no geometrical isomerism. Clear? Yes, come to this one. Again same problem, no chance for geometrical isomerism. CH2, CH2, CH2 and CH2. Or at least if you are trying from these carbon atoms, right? Here methyl group is given, here also methyl, methyl, again methyl, no geometrical isomerism, identical groups are given. And come to this one, yes, you can try with these two carbon atoms. What is the given substitution? Methyl and methyl. Okay. Next, what is the fourth valency? Fourth valency is hydrogen. Next one here also hydrogen. Is it possible? Yes. Methyl, hydrogen different. Methyl and hydrogen different. At least from 2 carbon atoms. If you are having proper substitution, then it can show geometrical isomerism. So directly I am going to these carbon atoms. sp3 carbon atoms, already given groups are methyl and methyl. What is the fourth valency? Hydrogen and hydrogen. Yes, this molecule shows geometrical isomerism. And try with these carbon atoms. We don't want CH2, CH3 and hydrogen given. Next one here, hydrogen and CH3. No problem. Next, from any 2 carbon atoms you can produce the geometrical isomerism. Why? Because for example, if you try with these 2 carbon atoms, here we don't want number of geometrical isomers, that we will calculate in the next class. Here the only question is which of the following molecule can show geometrical isomerism. Is it possible to produce geometrical isomers? Yes. Not only these 2, you can select these 2 carbon atoms, you can select these 2 carbon atoms, you can produce geometrical isomers. Come to this one, no problem. This molecule also shows geometrical isomerism. Now this one also shows geometrical isomerism. Why? Because from any 2 carbon atoms you select, yes, you have a proper substitution, just like methyl, hydrogen, hydrogen and methyl, hydrogen and methyl. Okay. Next, chlorine and chlorine given. Yes, select fourth valency, hydrogen, chlorine, hydrogen different, chlorine, hydrogen different. This molecule shows geometrical isomerism. Here hydrogen and bromine, hydrogen and bromine, hydrogen and bromine, no problem. Next one, here you select hydrogen and chlorine. Next one, hydrogen and bromine. These two are different, these two are different. Geometrical isomerism is possible. Okay, now these are the simple cyclic compounds, right? Sometimes they are giving combination of cyclic as well as double bonded systems. How to identify geometrical isomerism such type of compounds? For example, here let this type of molecule is given, okay, and here substitution like methyl and methyl, geometrical isomerism possible or not? And one more molecule I am giving. Yes, there is a 6-membered ring system, there is a double bond, right? Methyl and methyl, and here substitution given like this, CH3 and again CH3. Okay, let me give one more molecule. I am taking here 5-membered ring system, double bond, methyl and methyl. So what about geometrical isomerism in the given molecules, right? Now whenever combination of cyclic compound and a double bonded system is given, first you try with double bond. For example, now this is our double bond. Here what are the groups given? Methyl and methyl. At least on one sp2 carbon atom, if A is equals to B, let it is A and it is B, that means simply identical groups. Now there is no geometrical isomerism with respect to double bond. No geometrical isomerism with respect to double bond. Okay, the double bond is not responsible for geometrical isomerism. And for some time we forget about the double bond and come to the ring system. Here 4-membered ring system is there. Select this carbon atom, sp3 carbon, again sp3 carbon atom. Here what is the fourth valency? Hydrogen, and here methyl. Yes, these two are different. What is the fourth valency here? Hydrogen, and here methyl. These two are same or different? Different. Again here also different. Yes, with the help of ring system we can produce geometrical isomerism. Clear? Yes, there is no geometrical isomerism about the double bond, but ring is cooperating for geometrical isomerism according to the given substitution. Here also same situation. First you start from double bonded system. What is the group here? Methyl. Next one here also methyl. Same or different? They are same. No chance for geometrical isomerism. Double bond not cooperating for geometrical isomerism because of identical substitution on sp2 carbon atom. And come to the ring system. Whenever you are looking towards the ring system, inside the ring system, just you look at only sp3 carbon atoms. sp3 carbon, here also sp3 carbon atom. Already methyl groups are given and we are taking fourth valency hydrogen. Hydrogen, methyl. Methyl, hydrogen. Is it clear? Is it possible to produce geometrical isomerism? Yes, exactly, we can produce geometrical isomerism. Come to next molecule. Here double bonded system. First you try with double bonded system. Here what are the groups given? Methyl. Next one, methyl groups are there. Both are identical or non-identical? They are identical groups, methyl and methyl, right? There is no geometrical isomerism with respect to double bond. And come to the ring system. Yes, there is a methyl and methyl. On these carbon atoms, methyl. Next one, methyl, methyl. What is the fourth valency? Hydrogen. Here also hydrogen. Hydrogen, methyl. Methyl, hydrogen. These two same or different? Different. These two are also different. Now with respect to ring system, this molecule can show geometrical isomerism. Is it clear? This is the story about simple cyclic compounds. Okay, next one, geometrical isomerism. Geometrical isomerism. Geometrical isomerism in cycloalkenes. Geometrical isomerism in cycloalkenes. Very simple, cycloalkenes. Now in case of cycloalkenes, first you start with cyclopropene, basic example. For ring system minimum we require 3 carbon atoms. That is our cyclopropene. And what is the next molecule? Cyclobutene. Cyclobutene. 5-member ring system, cyclopentene. 6-member ring system, cyclohexene. And what is the 7-member ring system? Cycloheptene. 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 And what is 8-member ring system? Okay, this we will discuss later. Now just you look at these molecules: propene, butene, cyclopropene, cyclobutene, cyclopentene, cyclohexene, and cycloheptene. Okay, here first we are looking towards double bond. Why? Because here on this carbon atom, two hydrogen atoms are there. Is there any use of geometrical isomerism? Sorry, is there any use of two hydrogen atoms in geometrical isomerism? No use, right? Okay, come to that double bonded carbon atoms. Here I am taking like this. Yes, hydrogen and again hydrogen. Just you look at this molecule. These two hydrogen atoms present in same side or opposite side. Now these two are present in same side. In general, if both are present in same side, that is taken as what? Cis. So later we will give cis trans nomenclature. First here two hydrogen atoms are there, present in same side or opposite side. Same side, we call it as cis. Next one, if you want to write trans molecule, how to write trans molecule? Trans nothing but hydrogen and hydrogen, same side or opposite side, both are present in opposite direction. Clear? Cis nothing but hydrogen atoms are present in same side, or identical groups are present in same side. In case of trans, just I am trying to keep hydrogen atoms in opposite direction. Clear? Then how many carbon atoms left in this molecule totally? How many carbon atoms are there? We have 3 carbon atoms. 2 carbon atoms are bonded by double bond. 2 carbon atoms are part of double bonded system, and extra 1 carbon atom is there. So where we can arrange that carbon atom, third carbon atom? So now this kind of arrangement not possible. We cannot arrange that carbon atom. Okay, why? Because your molecule getting more and more strain. Simply we can say that now here trans molecule is not existing. Trans molecule is not existing. Only cis molecule is there. Isomers nothing but minimum we require how many molecules? Either single molecule or minimum 2 molecules. Isomers nothing but minimum we require 2 molecules. Here it exists in cis form, no problem. Hydrogen and hydrogen by keeping same side. Now we can say that that is a cis form, but there is no trans form. It has no other molecule to compare. Now here geometrical isomerism is ruled out. Not only cyclopropene, cyclobutene, pentene, hexene up to 7-member ring system. Up to 7-member ring system. No, very important, no geometrical isomerism about the double bond. Remember this point about the double bond. Whatever the substitution present on double bonded carbon atoms, I'm not going to talk about sp3. Sp3 we'll see later. Now whatever the substitution you are taking on double bonded carbon atoms, there is no geometrical isomerism up to what? Cycloheptene. Up to cycloheptene, no geometrical isomerism. Once again I am going to write same point, very important. Cyclopropene, cyclobutene, cyclopentene, next one cyclohexene and cycloheptene. Cycloheptene. These are very important molecules, right? Once again I am writing same statement that no geometrical isomerism, about the double bond. Whatever the substitution given about the double bond. Very important point. No geometrical isomerism about the double bond. For example, question given like this. Now 3-member ring system. They are giving methyl and methyl. And 4-member ring system. Okay, just like methyl and methyl. Any substitution given. 5-member ring system. Double bond. For example, here something like COOH is given, here also COOH is given. And let us take 6-member ring system. In 6-member ring system also, for example, here ethyl and ethyl groups are given. 7-member ring system, anywhere you can take double bond just like ethyl and ethyl group is given. What about geometrical isomerism in these molecules? Okay, so commonly observe, just I am taking from 3-membered ring to 7-member ring system. I am not going to keep any substitution on sp3 carbon atom, that you remember. Carefully observe, whatever the molecules I am selecting here from 3-membered ring to 7-membered ring system, just I am trying to arrange substitution on sp2 carbon atoms. I am not going to touch sp3 carbon atoms. Okay, here whatever the substitution given on sp2 carbon atoms up to 7-member ring system, is there any chance for geometrical isomerism? No geometrical isomerism. Same point. No geometrical isomerism about the double bond. Very, very important. Right. For example, now you observe this question. I am starting from 4-member ring system. Yes. Here I am taking methyl and methyl. On double bonded carbon atoms, methyl and methyl. Next one, on sp3 carbon atom, I am taking like this, methyl and methyl. Then what about geometrical isomerism? Now observe this molecule. Yes. What is geometrical isomerism in this molecule? Up to 7-member ring system, whatever the substitution given, completely you forget about the double bonded carbon atoms. Don't think about the double bonded carbon atoms. Why? Because we cannot produce it trans. Breaking of molecule will occur if you are changing into trans position. That is the main problem. Okay, because of more bond angle strain. So now from 3-member ring to 7-member ring system, 3-member ring to 7-member ring system, whatever the substitution given on double bonded carbon atoms, don't think about the geometrical isomerism. Here also same thing. We are not going to think about double bonded carbon atoms, but here you think about this sp3 carbon and sp3 carbon. From there we can produce geometrical isomerism. Now here what is the 4th valency? Hydrogen. Next, what is the 4th valency? Hydrogen. Okay, right. So according to this one, already given substitution methyl, and here also methyl. Methyl and hydrogen same or different? They are different. Methyl and hydrogen same or different? They are different. We can produce geometrical isomers. Very simple point. Okay, like that. Let me give another molecules now. Here I am taking that 5-member ring system. Yes, substitution given on double bond like ethyl and ethyl, and somewhere they are giving methyl and methyl. Next, another example, same 5-member ring system. Here methyl and methyl. Next one, methyl group is given. One more example by using 6-member ring system. Yes, ethyl and ethyl, methyl and methyl. For example, same 6-member ring system. Here chlorine and chlorine present. Next one, bromine and bromine given. Next, 6-member ring system. Here double bond. Here bromine. Next one, bromine given. Okay, these are the given molecules. Then what about geometrical isomerism in these molecules? First point, forget about double bonded carbon atoms. Up to 7-member ring system. Up to 7-member ring system, don't think about the double bonds irrespective of the given substitution. Whatever the substitution given, we don't want. Now come to these carbon atoms, sp3 carbon and sp3 carbon atom. Methyl given. What is the 4th valency? Hydrogen. Next one, here also 4th valency, hydrogen. Clear? Now here methyl and methyl. Methyl and methyl. Hydrogen, methyl, same or different? They are different. Methyl and hydrogen, same or different? They are different. Now we can produce geometrical isomerism. Okay. Now come to this one. Again, you don't think about the double bond. Forget, completely forget. Come to other carbon atoms. No carbon atom is supporting for geometrical isomerism. Why? Because here carbon atom with hydrogen and hydrogen, no use. Okay. And this carbon atom with hydrogen and hydrogen, no use. only one carbon atom containing different groups, but there is no another carbon atom. Minimum we require how many carbon atoms with proper substitution? Minimum 2 carbon atoms. That's why no use. And come to this one, first you eliminate double bond. We don't want double bond. And carbon atom, sp3 carbon, again sp3 carbon atom. So here hydrogen, next one methyl group, here hydrogen and methyl. Methyl hydrogen, yes, different. Methyl and hydrogen different. So we can produce geometrical isomers. Now come to this molecule. Now 6-membered ring system with a double bond. First close the double bonded system. We don't want the double bond. Forget about bromine, bromine double bond and everything. Now just you think about these two carbon atoms. These two carbon atoms. Okay. Chlorine given, what is the fourth valency? By default fourth valency hydrogen. Here also what is the fourth valency? Hydrogen. This molecule can exhibit geometrical isomerism. Why? Because hydrogen is different from chlorine and chlorine is different from hydrogen. Okay, right. Come to next one. First you close these double bonds. We don't want these two double bonds. Next one here bromine. What is the fourth valency? Hydrogen. Hydrogen and bromine. Same or different? They are different. Next one bromine and hydrogen. Same or different? They are different. This molecule can exhibit geometrical isomerism. Okay. That is a story about now cycloalkenes. Next one, another important example, very important, that is cyclooctene, 8-member ring system. Cyclooctene. Remember this point, very important. Cyclooctene. Cyclooctene. In cyclooctene, double bond can show geometrical isomerism. Okay. One second, let me check video. Yeah, clear. This is very good example, cyclooctene. What is the ring size? 8-membered ring. First I am writing normal planar form. This is the planar form with 8 carbon atoms. Now anywhere you can take double bond. Why? Because your molecule is symmetrical, right? That is cyclooctene molecule. And here what is the fourth valency? Hydrogen. Next one here also hydrogen. Clear? That is our cyclooctene molecule. For example, two hydrogen atoms are present in same side. We call it as cis form. Cis. If two identical groups are present in same side, that is taken as cis. And how to write trans form? So to write the trans form, here first I am going to write double bonded carbon atoms. Very easy to write, no problem. Clearly I am taking like this. Now double bonded carbon atoms. Here how many hydrogen atoms completed? Two hydrogen atoms, sorry, how many carbon atoms completed? Here two carbon atoms are completed like this. Okay, 1 and 2. Yes. Here we want to transform. Trans nothing but two hydrogen atoms should be in same side or opposite side. Two hydrogen atoms should be in opposite side. Okay, just I am writing like this, hydrogen and hydrogen. Very easy to write the trans form. First one here I am writing cis form and I am trying to write the trans form. First one to write the trans form, just I am keeping double bonded carbon atoms. Two carbon atoms I am selecting. These are part of double bond. And in trans form, how we are arranging hydrogen atoms? Same side or opposite side? These two hydrogen atoms should be in opposite side in trans form. Next one, how to arrange remaining 6 carbon atoms? How to arrange remaining 6 carbon atoms? To arrange remaining 6 carbon atoms, first at least you try to arrange 2 carbon atoms. Already 2 carbon atoms are completed. If 2 hydrogen atoms are present in opposite direction, then carbon atoms also present in opposite direction. Carbon, again here also carbon. Now till now how many carbon atoms completed? 4 carbon atoms completed. 2 are part of the double bond and remaining 2 carbon atoms we are taking in opposite direction. Just to write the trans form. Here how many carbon atoms completed? 4 carbon atoms are completed. Next, how many carbon atoms are left? 4 carbon atoms are left. These carbon atoms, just I am taking like this, carbon, again carbon. Okay. Next you connect like this, carbon and carbon. That is the trans form. Now this is what we call trans cyclooctane. Trans cyclooctane. And this one cis cyclooctane in double bond. Trans cyclo, sorry, this one cis cyclooctane and this molecule trans cyclooctane. Carefully observe these two molecules, very very important. Cis cyclooctane and trans cyclooctane. This cyclooctane molecule exhibits geometrical isomerism, very very important. So whenever double bonded carbon atoms are good, or double bond is given in 8-member ring system, this double bond can show geometrical isomerism. But up to 7-member ring system, 3, 4, 5, 6, 7, up to 7-member ring system, double bond never shows geometrical isomerism. But same double bond is part of 8-member ring system, that molecule shows geometrical isomerism. Okay, right. Come to next point. Once again I am writing like this, cyclo, again no need to repeat, just you look at the stability, wherefrom we observe geometrical isomerism about the double bond cyclooctane. Now cyclooctane, cyclononene, cyclodecene, 10 carbon atoms, cycloundecene, cyclododecene, and so on. Okay, right. How many carbon atoms present in cyclooctane? 8 carbon atoms are there. Cyclononene, 9 carbon atoms. Cyclodecene, 10 carbon atoms. Cycloundecene, 11 carbon atoms. Dodecene, 12 carbon atoms. Now stability point of view, now in case of cycloundecene, how many carbon atoms are there? 11 carbon atoms. Just you remember like this, 11 carbon atoms. Now approximate symbol I am using like this. Now here cis is approximately equals to trans. Now this is the stability order. In case of cycloundecene, what is the stability order? Cis approximately equals to trans. Next one, in these three molecules, now stability point of view, this is the stability of the molecules. Cis is greater than trans. Cis is greater than trans. Next one, 12-member ring system onwards, stability point of view, trans is greater than cis. That is the stability order. Okay, right. That is a story about cycloalkenes. So in cycloalkenes, wherefrom we observe geometrical isomerism about the double bond only from cyclooctane, 8-member ring system. Cyclooctane and cyclooctane onwards, 9-member ring system, 10-member ring system, 11, 12, whatever it may be, those molecules will show geometrical isomerism. That means double bond present in the ring system is responsible for geometrical isomerism. That can show geometrical isomerism. And if you want to give stability, now up to cyclodecene, what is the stability order? Cis is greater than trans. 11-member ring system is given, cis approximately equals to trans. Next one, 12 onwards, trans is greater than cis. Okay. Now just you tell me this point. For example, 8-member ring system is given, 8-member ring system, double bond also given, right? Next one, same 8-member ring system, 8-member ring system, double bond given. Next one, here some methyl groups are also given. Next one, 8-membered ring system, double bond given. Next methyl group is given. So what about geometrical isomerism in the first molecule? Come to first molecule. In the first molecule, this double bond can show geometrical isomerism. Why? Because what is the ring size? 8-member ring system. Substitution is not given on remaining sp3 carbon atoms, no problem. But here double bond can exhibit geometrical isomerism. That is available in the form of cis cyclooctane and trans cyclooctane. Come to next example. Double bond is responsible for geometrical isomerism or not? Yes, no problem. In 8-member ring system, this double bond can exhibit geometrical isomerism. That is one segment for geometrical isomerism. Come to this one, here also segments are there. sp3 carbon atoms, methyl, hydrogen, yes. Next one, hydrogen and methyl. Same or different? Different. Again, these two are also different. This is also one particular segment for geometrical isomerism. Overall, this molecule shows geometrical isomerism. Come to next molecule. Here, 8-member ring system, and here hydrogen atom is there. Hydrogen, right? Here methyl group is present. So once double bond is present, now this molecule can show geometrical isomerism. Why? Because that double bond is part of which ring system? 7-member ring system or 8-member ring system? That is part of 8-member ring system. Very important examples. Okay. A few more molecules I am giving, right? For example, N double bond N, CH3 and CH3 given. N double bond N, phenyl and phenyl given. N double bond N, ethyl and ethyl given. Okay, right? Yes. Now just to look at this one. Diazo compounds, I think right now not possible to discuss about spiro compounds. That we will see in the next class. Now tell me, these molecules geometrical isomerism possible or not? Even sometimes they are giving cyclic compounds like this. Here hydrogen and hydrogen from cyclic compounds. Yeah. Next, methyl and methyl. Next, nitrogen, hydrogen, okay, and simple hydrogen molecule N2H2. Yeah. Tell me about geometrical isomerism in these molecules. Which color? Yeah, better. Come to first molecule. There is a restricted rotation of bond. That means double bond. Here lone pair of electron is present. Here also lone pair of electron is present. For example, if it is considered as a group, lone pair and methyl, same or different? Different. Methyl and lone pair different. This molecule can show geometrical isomerism. Like that here, lone pair of electron, right? Phenyl, lone pair, phenyl and lone pair. Like that. This molecule also shows geometrical isomerism. Now come to this example, same thing here, lone pair, next lone pair, hydrogen, lone pair, different, hydrogen, lone pair, different, geometrical isomerism. Next one here, I am taking like this, lone pair, methyl, and nitrogen, lone pair, and methyl, same or different? Different. This molecule also shows geometrical isomerism. Same thing they are giving like this, hydrogen. Now you select lone pair of electron, here also lone pair of electron. Okay. And what is the last example? Hydrogen molecule N2H2. N2H2. How many nitrogen atoms are there? 2 nitrogen atoms are there. Hydrogen and hydrogen. And here lone pair. Next one, lone pair of electron. Lone pair of electron. Is it possible? Yes. This molecule also shows geometrical isomerism. Okay, so these are the best examples, and just you tell me last one about geometrical isomerism. For example, here double bonded system is given here NH, NH, okay. Here geometrical isomerism possible or not? Last question, just you tell me this point. Geometrical isomerism possible or not? For example, these two are looking like same. For example, if you are trying to explain about the double bond, so right side groups looking like same or different? They are same. Left side, these groups are same. Geometrical isomerism possible or not? Now you remember one point. Whenever question is given on geometrical isomerism, simply you don't stop at a double bond. First you verify about the double bond. If double bond is not going to show geometrical isomerism, then you go for ring also. For example, if you start from this carbon, hydrogen, and this entire group, nitrogen, hydrogen, next here, lone pair of electrons. Now this is the segment for geometrical isomerism. Like that, lone pair of electron and here hydrogen. This is also segment for geometrical isomerism. And come to this one, no doubt double bond, no geometrical isomerism. But come to other ring systems, here lone pair of electron, segment for geometrical isomerism, here also segment for geometrical isomerism. Next one, lone pair of electrons and here hydrogen. Now finally this molecule shows geometrical isomerism or not? Yes, this molecule shows geometrical isomerism. So how many geometrical isomers are possible, that we will see in the next class. Okay, right. So now till now cycloalkanes completed, cycloalkenes are also completed. At least in the next session, in the next class, we will try to complete calculation of geometrical isomerism in different compounds. Next, aldenes, biphenyls and spiro compounds. Okay, thank you.